Hi there. Welcome to my channel. I'm Thomas, and I do educational videos on many subjects, although we are locked in right now on studying up on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson put together a system of theory. So this is a theory of everything that is self-serve. If you understand the theory, you can use it yourself, and you can come up with answers in any subject field that you'd like if you know how to use the theory. The basic idea is that we live in a universe of motion. The universe is not made out of matter. It's not made out of energy. It is made out of motion. And motion is the relationship between space and time. Space and time are not the container of the universe. Rather, they are the contents of the universe. The universe is made out of space and time, otherwise known as motion. Motion is basically a fraction with space and time, space or time as the numerator, and time or space as the denominator. And time and space both have their coordinate aspects, meaning they have 3 or more dimensions. And they also have their clock aspects, meaning that they progress. They're always getting, in time's case, they're always getting later and later. In space case, it's always getting farther and farther apart. Time and space also both come in discrete units, meaning there's a minimum unit of space and a minimum unit of time. 1 unit of space in 1 unit of time is the speed of light, which makes sense. That's 1 over 1 equals 1. The speed of light is the origin or the background or the 0 point of the universe. In the reciprocal systems, measurements are made from the speed of light, not from 0, but from what he calls unit speed. So are they faster than the speed of light or slower? Einstein's conclusion that the speed of light was the maximum speed of the universe is only applicable to the half of the universe that's moving slower than the speed of light. There's also, which Larson calls the material sector. There's also a half of the universe that moves faster than the speed of light. Larson calls that the cosmic sector. And Einstein didn't know anything about that. And Larson says that, even though we don't know anything about this cosmic universe that moves faster than the speed of light, we do actually, and we can figure out things exactly through extrapolation because of the reciprocal relationship between space and time. When you have a fraction such as, say, 2/3, the reciprocal of that is 3/2. They have the same qualities, but they're just inverted. And that's the same with the material sector and the cosmic sector. So all you have to do is invert the roles of space and time, and you get exactly what's going on in the cosmic universe. If you know what's going on in the material universe, you can extrapolate to the cosmic universe simply by inverting. And Larson started working on this way back in about 1930, and he continued up until he died in 1990. We're looking at his 1979 book right now, which is called Nothing But Motion. Covers mostly physics and a little bit of organic chemistry. He also, delved into many other subjects, including chemistry and astronomy and economics and metaphysics, including religion, philosophy, psychology, dream interpretation. And I think had he lived longer, he would have gone into many other subjects. And some of his followers have gone along, especially Dr. Bruce Perret, and got into all kinds of crazy stuff, a lot of crypto history, conspiracy theories, and so on. Now, we will look at all those things in the future. But right now, we're looking at this nothing but motion. We're about to wrap up his 7th chapter, which is called high-speed motion. And so high-speed motion is basically about his critiques of relativity theory and how he basically demonstrates that relativity theory is, pretty much a crock. And that what he's kind of going over here at the end is that, Einstein basically tried to force this on us by saying there is no alternative, where all of these, the equations came out wrong. Time was moving more slowly than it was supposed to, or faster than it was supposed to, or, and Einstein basically saying that, we have to accept this special theory of relativity because there's no other way. That is, so far from what science is supposed to be that, Einstein should have been laughed out of the laboratory. But instead, we put him up on a pedestal and said, this is one of the people that you can't touch. There's, Einstein and Shakespeare and Mozart, and you can't touch these people, and they're all complete hacks. But we're just dealing with Einstein right now. Maybe Mozart wasn't a complete hack, but he was, I think, pretty clearly a victim of satanic ritual abuse. And so that's why he was composing symphonies at age 5. Okay, we're going to just wrap up the end here and then move along. In contribution, in the form of the special theory, it can be accurately evaluated only if it is realized that this too is a fudge, the special theory, that is. A conceptual fudge, we might call it. As he explains in the statement that has been our principal target in this chapter, what he has done is to eliminate the metrical meaning of spatial coordinates. That is, he takes care of the discrepancy between the two measurements by arbitrarily decreeing that one of them shall be disregarded. This may have served a certain purpose in the past by enabling the scientific community to avoid the embarrassment of having to admit inability to find any explanation for the high-speed discrepancy. But the time has now come to look at the situation squarely and to recognize that the relativity concept is erroneous. It is not always appreciated that the mathematical fudge accomplished by the use of the Lorentz equations works in both directions. If the velocity is not directly determined by the change in coordinate position during a given time interval, it follows that the change in coordinate position is not directly determined by the velocity. Recognition of this point will clear up any question as to a possible conflict between the conclusions of Chapter 5 and the constant speed of light. In closing this discussion of the high-speed problem, it is appropriate to point out that the identification of the missing factor in the motion equations, the additional time component that becomes significant at high speeds, does not merely provide a new and better explanation of the existing discrepancy. It eliminates that discrepancy, restoring the metrical meaning of the coordinate distances in a way that makes them entirely consistent with the constant speed of light. Okay, that's the end of Chapter 7. Now, basically, this is just Occam's razor, Larson's solution to the problem is just much, much simpler than the relativists' solution. And that's just on the surface. If you go deeper into it, you know, it becomes more and more simple. He doesn't require you getting rid of any of the kind of the sacred cows or whatever, you know, that space and time, you know, just, you know, arbitrarily shrink and expand, and they just so happen to fit the, you know, fit the equations just so happen to fit the things that they're being plugged into. And if they don't, then we insert another constant or something, some other, what Larson calls a fudge factor, to, you know, make the numbers work out. You know, back in the day, those were called epicycles that were used by the Ptolemies and other ancient astronomers, Aristotle, to, you know, account for planetary motion that didn't make sense. And, you know, that could all be a fable as well, but that's the fable that we've been taught, is that they ended up adding all kinds of supplemental rotations on the bodies, of heavenly bodies, to be able to explain retrograde motion and the like. And somehow they're able to justify these things in their head. Okay, now we'll move on to Chapter 8, which is called Motion in Time. Okay, so this is where we're talking about either the cosmic sector, we're talking about motion that's moving faster than the speed of light. And, you know, if you go beyond the speed of light, motion moves into time instead of space, is the idea. But we'll let Mr. Larson explain it himself. Motion in Time, Chapter 8. The starting point for an examination of the nature of motion in time is a recognition of the status of unit speed as the natural datum, the zero level of physical activity. We are able to deal with speeds measured from some arbitrary zero in our everyday life because they are not primary quantities. They are merely speed differences. For example, where the speed limit is 50 miles per hour, this does not mean that an automobile is prohibited from moving at any faster rate. It merely means that the difference between the speed of the vehicle and the speed of the portion of the Earth's surface over which the vehicle is traveling must not exceed 50 miles per hour. The car and the Earth's surface are jointly moving at higher speeds in several different directions. But these are of no concern to us for ordinary purposes. We deal only with the differences and the datum from which the measurement is made. And the datum from which the measurement is made has no special significance. In current practice, we regard a greater rate of change in vehicle location relative to the local frame of reference as being the result of a greater speed, that quantity being measured from zero. We could equally well measure from some arbitrary non-zero level, as we do in the common systems of temperature measurement. Or we could even measure the inverse of speed from some selected datum level. And we attribute the greater rate of change of position to less inverse speed. In dealing with the basic phenomena of the universe, however, we are dealing with absolute speeds, not merely speed differences. And for this purpose, it is necessary to recognize that the datum level of the natural system of reference is unity, not zero. Unity meaning the speed of light. Since motion exists only in units, according to the postulates that define the universe of motion, And each unit of motion consists of 1 unit of space in association with 1 unit of time. All motion takes place at unit speed from the standpoint of the individual units. This speed may, however, be either positive or negative, and by a sequence of reversals of the progression of either space or time, while the other component continues progressing unidirectionally. An effective scalar speed of 1 over n, or n over 1, is produced. Now recall a scalar speed means a speed that has a magnitude but it has no direction. And it's visualized by using a balloon with a magic marker, a bunch of dots on the balloon. You blow up the balloon and all the dots are moving away from each other, but in no particular direction. This is an outward scalar motion. You suck in the balloon, all the dots are moving toward each other. This is an inward scalar motion. So the only direction that scalar motion has is in or out, but no particular direction, no vectorial direction. And scalar motion is the main foundation of Larson's system of a universe of motion. Okay, so an effective scalar speed of 1 over n, or n over 1, is produced. In Chapter 4, we considered the case in which the vectorial direction of the motion reversed at each end of a 1-unit path, the result being a vibrational motion. Alternatively, the vectorial direction may reverse in unison with the scalar direction. In this case, space, or time, progresses 1 unit in the context of a fixed reference system, while time, or space, progresses n units. Here, the result is a translatory motion at a speed of 1 over n, or n over 1 units. The scalar situation is the same in both cases. A regular pattern of reversals results in a space-time ratio of 1 over n, or n over 1. In the example shown in the tabulation in Chapter 4, where the space-time ratio is 1/3, there is a 1-unit inward motion followed by an outward unit and a second inward unit. The net inward motion in the 3-unit sequence is 1 unit. A continuous succession of similar 3-unit sequences then follows. As indicated in the accompanying tabulation, the scalar direction of the last unit of each sequence is inward. Okay, he has a table here, and it just says direction, and then he's got a number, unit, 1, 2, 3, 4, 5, 6. Okay, for the scalar motion, if we're talking about vibratory motion, for scalar motion, it's inward, outward, inward, inward, outward, inward. So that's 1/3, because it takes 3 units to actually go 1 unit inward. Inward, outward, inward, outward, inward. So that's a net of 1 inward. And then it goes inward, outward, inward again. Now, if this is vectorial, then it's right, left, right, left, right, left. And so that creates a vibratory motion, those combinations. But if you have a translational motion, on the scalar level, you have inward, outward, inward, inward, outward, inward. But the vectorial motion there is forward, backward, forward, forward, backward, forward. So, you know, when you have the vibratory motion, you have, you know, an alternation, right, left, right, left, right, left. Whereas if you have the translational motion, you don't. You have this 1/3 situation, forward, backward, forward, forward, backward, forward, which matches up with inward, outward, inward, inward, outward, inward. So they're matched up. But if you have a vibratory motion, they go opposite, they alternate. Now, as we will find out, this whole concept of Larson's here is rejected by some of his followers, and they have a different proposal for how these different motions come about, this vibratory motion. Okay, but we will let Larson explain himself before we get into these other people. Okay, as indicated in the accompanying tabulation, the scalar direction of the last unit of each sequence is inward. A sequence involving an even number of alternates, n-1 and n+1. For instance, instead of two 4-unit sequences in which the last unit of each sequence would be outward, there is a 3-unit sequence and a 5-unit sequence. The scalar direction of the first unit of each new sequence is also inward. Thus, there is no reversal of scalar direction at the point where the new sequence begins. In the vibrational situation, the vectorial direction continues the regular succession of intervals, even at the points where the scalar direction does not reverse. But in the translational situation, the reversals of vectorial direction conform to those of the scalar direction. Consequently, the path of vibration remains in a fixed location in the dimension of the oscillation, whereas the path of translation moves forward at the scalar space-time ratio 1/n or n/1. This is the pattern followed by certain scalar motions that will be discussed later, and by all vectorial motions, motions of material units and aggregates. Okay, that will do it for today, and we will catch up here with Larson discussing motion in time when we return tomorrow. Thanks for tuning in, and have a great day.